let's imagine that I am going to go and survey 100 random people that are in the building right now. Going to go into maybe pick one random person at each classroom. Maybe it's stratified. Maybe it's just a completely random sample. Maybe I'll just go into the lobby and randomly pick people out of the lobby. Let's say I'm going to go around and pick out like a random sample of 100 people, and I'm going to ask them their height, for instance. Okay, what I'm going to wind up with is I'm going to wind up with a list of numbers, right? So I'm going to wind up with 60 inches and 72 inches and 66 inches and so on and so forth. So I have 100 numbers, right? Now, for a moment, let's assume that heights are normally distributed. In other words, the nature of heights is that if I were to draw a histogram of all these 100 numbers, they would look something like this. The most common outcome would be a weight kind of in the middle. Maybe, let's see, that's 5 feet. Let's say maybe this would be like 65 to 70 inches. Okay, and maybe the next most common might be a little bit shorter than that, or a little bit taller than that, but not as common as the most likely height, the average height. And then if I go a little bit further down to under 60 inches, be less common and less common. Very short people, very, very short people would become less and less common. Okay, so we've kind of seen that kind of distribution before, right? It's kind of what, if I kind of fit a curve to this, it's bell-shaped, right? And this is what we call normal distribution. It's unlikely that heights are really perfectly normally distributed. In other words, maybe it's more likely you might have more extreme short heights than really extreme tall heights. Maybe the tail is a little bit different. But for our purposes right now, we're going to assume that heights are normally distributed. And if we picked any individual in this building right now, and we asked them what their height was, well, if the average height is 68 inches, I would expect that the chances that one person I picked out at random, there's a 50% chance that he would be less than 68 inches, and a 60% chance he would be more than 68 inches, right? And out of those 100 people that I selected, the most likely outcome would be that 50 of them would be below 68 inches, and 50 would be above 68 inches. So, in other words, the average height, and when I said 50 above and 50 below, what am I looking at there? I'm not looking at the mean, but I'm looking at the median. The median and the mean are exactly the same. They're right in the middle. And now, if I were to take that, instead of taking a sample of 100 people, I took all of the people in all of the schools of CUNY, and I drew another histogram. Well, there would be so many people that I would get a much smoother curve, a much smoother histogram. And eventually, if it's a very, very, very large population, I would get something that almost looks like a perfect histogram if it's a perfect bell curve, if it's a truly normal distribution. Well, we can represent that mathematically, right? This bell curve, we have a formula that determines what the height is at any point on this bell curve, like at 60 inches, at 73 inches, what the probability of that particular outcome is. That's what the height of that bell curve represents. The areas in this bell curve represent the probabilities that any of the weights are within that region. So the entire bell curve, right, this entire normal distribution represents 100% of the population, right? And of that 100% of the population, 50% of the population is going to be below the mean or median height, and 50% is going to be above the median height, right? Seems pretty straightforward, right? Well, we're going to take it a step further now. Okay, in fact, because we can represent this with a formula, this distribution is based on probabilities. Probability that given it's normally distributed, that a certain number of people would be taller or higher, but shorter or taller than the median, and so on and so forth. this is all based on a formula that we can use to determine these areas in this distribution. And if I'm going to redraw this distribution, this represents heights. And the average height is, let's say the average height is 68 inches. And that would be the average height. And beyond that, I can tell that, well, 50% of this is below, of the population is going to be below 68 inches, 50% is going to be above 68 inches. I'm sorry. Oh, my goodness. Oh, there we go. Okay. Okay. So 68% is below, is the median and the mean, at 50% of the population. Below that, 50% is above that. I'm going to draw another distribution. And this distribution is a distribution of body temperatures. Okay, and in this case, it's also a bell-shaped curve, but the mean is 98.6 degrees. And the highest temperature I would expect to have in a random in the population might be 107 degrees. Maybe the lowest temperature I might expect to have is going to be maybe 89 degrees, right? So the middle is a different number than this one is. But notice the shapes of these distributions are the same. Okay, so the middle is the mean, right? 50% below, 50% above. But what distinguishes the heights? This could go anywhere from, say, 40 inches to 96 inches. Let's say the heights have those numbers have a much wider spread, don't they? Right? And in statistics, how do we describe that variability of that spread? What do we call that? Right? Remember what it was? What function we used for that? The standard deviation. Okay. Now, interestingly enough, because these follow a path that's based on that formula, based on the probabilities of these outcomes for a normally distributed population. Because of that, these areas underneath this curve are predictable. And for instance, I can tell you that within one standard deviation below the mean and one standard deviation above the mean, we would expect to find 68% of that population. Okay, so let's say that the standard deviation here, sigma, population standard deviation, is equal to 6 inches, right? What's one standard deviation below the mean if the mean is 68 inches? It's 62 inches, right? What's one standard deviation above the mean? It's going to be 74 inches, right? So we would expect 68% of the population to have a height between 62 inches and 74 inches in this particular population. How do we deduce that? We deduce that by knowing what the mean was, the center was, and what the variability was, what the standard deviation was. Okay. So that's pretty interesting. But now let's take a look at the temperatures, body temperatures. Okay. So we take a look at body temperatures.
Sorry, I'm trying to mute you.
I may okay. I should be able to mute you from up here. For some reason, sometimes it works and sometimes it doesn't. Okay, so let's take a look at that body temperature example. Now, the mean here is a different number. So it's 98.6. And these numbers are not as variable, are they? Right? The range is not as wide as the heights were. Let's say that the standard deviation for the temperatures is maybe, let's call it 2 degrees Fahrenheit. Okay. So 68% of the people in this population are going to have a body temperature between what degree and what degree? 2 degrees below, 96.6, and 2 degrees above, which is 100.6, right? So 68% of that population is going to be within that range. What do we have in common here? Well, the mean is different, the standard deviation is different, but the distribution, the probability distribution that we call a normal distribution, based on the mean and the standard deviation, we can predict how much of the population is within that range. Okay, so we have a kind of a quick way of estimating what these areas are, and we call that the empirical rule. And we're going to take a look at the empirical rule. In the empirical rule, we're predicting that 68% of the population is between 1 standard deviation below the mean and 1 standard deviation above the mean. Depending on the particular population you're working with, the mean and the standard deviation are going to be different each time, right? So for height, it's going to be one thing. For blood pressure, it's going to be something else, and so on and so forth. But that relationship stays the same, assuming that it's a normally distributed variable in the population. Okay, now, even beyond that, though, 2 standard deviations above the mean to 2 standard deviations above the mean represents about 95% of the population. I'm going to sketch this because this one's a little bit harder to read than I want it to be. Okay, so here's my normal distribution again. Except this time I'm not going to bother to put in particular numbers. I'm just going to say the center is the mean. And the standard deviation, I'm going to call that the number of standard deviations above and below the mean. So 1 standard deviation below the mean to 1 standard deviation above the mean is approximately 68% of the population. So that's going to be minus 1 standard deviation plus 1 standard deviation. Now, if the mean is 100 and the standard deviation is 10, that's going to be 90, 100, and 110, right? So instead of defining it with instead of describing it with the actual numbers, I'm going to describe it with just the number of standard deviations. In another distribution, if the mean is 50 and the standard deviation is 2, this would be 48, 50, and 52, right? Doesn't really matter. But this minus 1 represents the number of standard deviations for any population, any normally distributed population. We call that number the z-score, or in other words, the number of standard deviations above the mean or below the mean. If it's below the mean, we call it a negative number, negative 1 standard deviation. If it's above the mean, we call it a positive number, plus 1 standard deviation. So if I go to 2 standard deviations below the mean and 2 standard deviations above the mean, right? What percentage of the population am I dealing with now? 95%, roughly 95% of the population, right? How about 3 standard deviations? Plus 3 to minus 3 is going to be, that's now going to represent 99.7% of the population. Okay, almost the entire population is within 3 standard deviations in a true normal distribution. Okay, now that means we can do a lot. We can examine this, and it lets us understand quite a bit about the distribution, the probabilities of selecting people randomly in a normally distributed population. So I'm going to go back to that document. Okay, and in this document, it's a little bit more precise here. Well, that says 68%. You can see it's really 34.1 and so on and so forth. But you want to know something? Notice in particular, 2 standard deviations below the mean to 2 standard deviations above the mean. That represented 95% of the population, right? A lot of times in statistics, we are dealing with situations where there are always going to be outcomes or events that happen very rarely, either far away from the mean below, far away from the mean above. But we're mostly focused on what happens a bit more consistently, right? And that 95% is kind of a magic number for us, right? So knowing that 95% of the population is within this range really helps us understand how this population is distributed. So that 95% is important to us. It's going to come up again quite a bit as we work through this stuff. Okay, so let's take a look at this. So in this document, we have some examples that we can apply. Okay, so let's start off with heights again. Assume that the heights of adult Caucasian men have a mean of 68 inches and a standard deviation of 4 inches. What's the probability that a randomly chosen individual chosen from this population has a height greater than 68 inches? What's the mean? Mean 68 inches, right? So what's the probability that you would randomly choose someone that's taller than 68 inches? It's 50%. He's either going to be taller or short. You know, there is the chance that he could be exactly 68.000000 inches, but realistically, you know, if it's a continuous scale, he's not going to be exactly 68 inches. It could be below. If the chance of him being below or above 68 inches is equal, right? So 50% chance he's going to be greater than 68 inches. 50% chance he's going to be less than 68 inches. Okay, and we see this here. Okay, let's draw this distribution. .68 inches, and the standard deviation, what was it again, 2 or 4? 4, okay, 4 inches. Okay, so 50%, what's the probability that he's going to be taller than 68 inches? Well, that's that area in here, 50% of the population is greater than 68 inches. So 50% chance we're going to select him. Okay, let's go back and look at the next part of this. What's the probability that he's going to be between 64 and 72 inches tall? .64 and 72 inches tall. What's the probability that he's going to be between these two heights? It's going to be this area. This area represents the probability or probability density of that outcome, right? Well, how many standard deviations below the mean is 64? -1, right? -1. How many standard deviations above the mean is 72? +1. So 1 standard deviation below the 1 standard. What is this area here? 68%, right? So the probability of selecting someone that's between 64 and 72 inches in this population is 68%, 0.68, right? Okay, so let's go back and do this again. Let's go back again. Oh, no, it won't let me undo it that way. Oh. Okay. Okay, what's the probability that it's going to be between 60 inches and 76 inches? Probability is going to be between 60 inches and 70, how many inches did I say? 76 inches. Okay, so that would be 2 standard deviations below, right? 8 below 68 is 60, 8 above 68 is 76, to 2 standard deviations above, right? So what's that probability? 95%, right? So chances are 95% that if I randomly choose an individual from this population, he's going to be between 60 inches and 76 inches. If I asked you, what's the probability that I would pick a person from this population that is not between 60 inches and 76 inches, what would that probability be? Right? He's not between those two numbers. What's the probability? What's left? 5%. It's 5% chance he's going to be shorter or taller than 68 inches and 76 inches, right? So think about how powerful this is. Think about how much this tells us about a population. Okay, so let's move on to another question. See how we work there. Assume the heights of adult Caucasian women has a mean of 63 inches and a standard deviation of 3 inches. What percentage of the women in this population have a height greater than 63 inches? The mean is 63, 50%. Great, okay. Greater than 66 inches. Uh-oh, let's take a look at this. Let me get a fresh piece of paper here. Okay, so it always helps kind of to sketch this stuff out, especially in the beginning. Not a very neat normal distribution, but this was 63 and the standard deviation was 3. And what did I ask? What's the probability that a woman, randomly select woman would be, did I say greater than 66 inches? Greater than 66 inches. Okay, 66 inches. Okay, so now I'm interested in the probability of selecting someone that's above 66 inches, that's in this part of this probability distribution, right? So let's think about this. Using the empirical formula, I know that this is plus 1 standard deviation, minus 1 standard deviation. This area in here would be 68%. Well, one of the properties of the normal distribution is it's symmetrical, right? You can flip it over, it's mirror image, you can fold over on itself, right? So if this is 68%, what's the area in here? 34%, right? What's the area in here? 34%. So this area from the mean and above is 50%, and this area is 34%. How much is left? Right, 16%. Actually, some of you are giving me a more accurate answer because you're looking at the better version of this on this document, right? So the probability of randomly selecting a woman from this population that's above 66 inches is 16%. Okay, so let's take a look at the next question we have on here. Okay, what's the probability of selecting a woman that's less than 60 inches tall? Okay, so 60 inches would be here. So we're talking about this area in here. What would that area be? 16% also, right? Let me ask you another question. What's the probability of selecting a woman that's less than, less than 57 inches tall? That would be that little area in there, right? How many standard deviations below is 57 inches? Minus 2. And if I went to 69 inches, it'd be plus 2. So this area in here is 95%. What does that leave down at the bottom there? 2.5, well, at least 5% total at each end, right? But this end is only 2.5%. So the probability of selecting someone that's less than 57 inches tall is 2.5%. Probability of selecting someone who's bigger than 27 inches, that bigger than 69 inches tall, is also 2.5%. Okay, so the probability of selecting someone that's outside of 2 standard deviations is 2.5% on the low side, 2.5% is 5% total. And so, oh, interesting. Okay, so now let's take a look at the next one. Okay, gestation time for humans has a mean of 266 days. Now I know some of these things are not truly completely normal, but for our purposes, we're going to assume that they're completely normal for now. Has a mean of 266 days and a standard deviation of 25 days. What percentage of pregnancies would you expect to be greater than 291 days? Okay, so mean of 266, standard deviation of 25. So again, I'm going to draw my normal distribution. And my mean is 266 days. My standard deviation is 25. And I want to know what's probability that a pregnancy would be greater than 291 days. So how many standard deviations above 266 is 291? One standard deviation. One way you can figure that out is you can say to yourself, remember we call number of standard deviations the z-score. You can say the z-score is equal to the value you're interested in, x, minus the mean over the standard deviation. So that's going to be 291 minus 266 over 25. And of course, that turns out to be 25 over 25. So it comes out to be 1, right? In fact, it comes out to be positive 1 because the x, the 291, is greater than the mean. Had it been, had we been looking on the other side, we would wound up with a negative number, but which is right because we would expect a negative z-score. So that's 1 standard deviation above. What do we say that area is going to be? Right, it's going to be about 16%, right? Right, because this is going to be 34, and if we had 1 standard deviation below, it would be 34. So that would leave 16% above 1 standard deviation. Okay, let's take a look. The next question is less than 241 days. Again, pretty convenient here because that's going to be pretty easy. So z is equal to 241 minus 266 over 25, x minus the mean over the standard deviation is equal to minus 25 over 25 is equal to minus 1. So that's minus 1 standard deviation. The probability of being less than that is, again, 16%. Okay, so if we get numbers that are a little bit odd, we can take advantage of this simple formula to figure out what the z-score is, if the numbers get a little challenging. Lastly, what's the probability of being of a pregnancy being less than 241 days or greater than 291 days? So what are those areas? That's going to be less than 241 days and greater than 291 days. So it's the probability of a pregnancy being shorter than 241 or greater than 291. It's going to be the sum of those two areas, right? So it's going to be roughly 32%. Okay. Everybody comfortable with that? That's pretty simple, right? Okay. As always, we take something simple. Well, now we're going to make it a little bit more complicated, right? You were anticipating that, I hope, right? Okay. So now that we know, now we can figure this out simply. Let's make this a little bit more complicated. I think the first example here actually just kind of reiterates what we just did, but we'll do it anyway. Okay. Okay, assume that the heights of U.S. women, that's the same, roughly, it's a little bit different, actually. Assume that the heights of adult U.S. women have a mean of 63 inches and a standard deviation of 2. What percentage of women would you expect to have a mean less than 63 inches? 50%, right? Okay, how about less than 62 inches? Oh, things are going to get a little thorny here now. Okay, let's draw this. Here's our normal distribution. The mean was, what did I say the mean was? 63. 63, and the standard deviation is 2. And now I want to know what percentage of women are less than 62 inches tall. 62 inches tall. Okay, so now where's one standard deviation below the mean? Is 63 is going to be 61. So 62 is not actually an even number of standard deviations above the mean or below the mean, right? So it's kind of tough for me to apply that rule, that simple empirical rule that we had before that was dealing with whole numbers of standard deviations, right? So instead, I'm going to use my formula. Z is equal to x minus mu over sigma, and z is equal to 62 minus 63 over 2. So z is equal to negative 0.5, negative 0.5. It's half a standard deviation below the mean. Well, now my empirical formula doesn't tell me what area that this represents, does it? So I need another mechanism for doing this. And in fact, there is another way you can do this. We have tables in your open intro textbook. You have a table on Blackboard. I have a series of tables posted as well. I'm going to go to those tables right now, called the Z table. Oh, there it is. Okay, I like to use this one. This is from a textbook that we used to use a while ago. It's pretty. It's got the school colors, which are purple. So I like this table, right? It's almost like it's identical to the tables in your textbook, right? So we can be a little aesthetic here. Just because it's math doesn't mean you can't appreciate, a little the art of this as well, right? So this table tells us what areas are represented under this distribution with a lot more refinement than the empirical formula tells us. And the deal here is we really have two tables here. This table represents all the areas below the mean, and you'll notice that where it says Z or X over here, that's really where it says Z over there. If you scroll down here, all those are all negative numbers. Those all represent Z scores below the mean. Okay, and if you go down here, 0.00 is 50%, 0.5. That area, in other words, the Z-score, and the Z-score is 0, right? It's neither negative or positive, but this table shows that represents 50%. In fact, you see the shaded area over here? That represents the area that you're getting from this table. If I scroll up, there's a second page of this table. And it shows the areas for z-scores that are above 1, above 0, right? All positive. In other words, they're on the right side of the mean. Both of these tables have the areas in the distribution in the center here. And on the first column and on the top row, there are numbers that represent the z-score. Now, it represents the z-score to 3 digits, right? So, for instance, our z-score would be 0.50, but negative, right? Negative 0.50. It's negative 1/2. So, if I were going to look that up on here, I would go to negative 0.5. And if I look across this row, the third digit, there are 10 columns here. Each one of those columns represents the third digit. So 0.50 is 30.85, and 0.51 is 0.3050, and 30.52, 3, 4, 5, 6. If you look at the top, it represents 0.01, 0.02 represents the third digit. So this is a convenient way for you to look up in a small table without using up pages and pages, keeping it compact, what the z-score is for what the area is that represents a 3-digit z-score. Okay, so negative 0.050 is 0.3085, or 30.85%. So what does that mean? That means that the area to the left of that z-score, it's always the area to the left. The area below or to the left of that z-score is 0.3085. So if I go back to my table here, where have I put it? Did I draw it? There it is. Okay. If I go back to my table here, oops. If I go back here, this area from here, from 62, which is negative, z-score negative 0.5, this area from here down represents 0.3085, right? If I describe it as a percentage, it would be 30.85%, right? But you can already see that this is going to get a little cumbersome to start to use this percentages. Let's kind of most of the time describe them as probabilities. So the probability of randomly selecting a woman that has a height below 62 inches is 0.3085, right? Or I'm gonna cheat a little bit, about 31%. What's the probability of selecting a woman whose height is greater than 62 inches? It's 1 minus that, right? 1 minus 0.30. In other words, 1 minus 31%, I'm going to call it, and that would be 69%, right? Interesting, right? What's the probability of selecting a woman that's between 62 and 63 inches tall? Well, this area is 50%. That's the mean, 63 inches. And this area is 31%. So what does that leave for this area in here? Right? Leaves what, 19%, right? 9 or 19%. Everybody comfortable with that? See how we can manipulate this to figure out what all these probabilities are? Okay, good. So what was the next part of this question? Okay, what's the probability of selecting a woman whose height is greater than 66 inches? Oh, this is going to get a little thorny now. Okay. Actually, you know what I'm going to do? I'm going to draw a new one, because I've kind of written all over this thing. I just want to keep it clear. Okay, so again, my normal distribution. And my mean was, what I said, 63 inches, right? And my standard deviation was 2 inches. And now I want to know what's the probability of selecting a woman who is taller than 66 inches. So what's the z-score for 66 inches? 66 minus 63 over 2 is equal to positive 1.50, right? That's my z-score. Okay, so now that's a positive number, so I have to use the second page, don't I? Okay, so let's use the second page here, which is all positive numbers. So positive, a z-score positive 1.50 would be 0.9332, about 93%, 0.9332. But what area does that represent? That represents the area to the left of that z-score, right? So I'm going to go back here. So now I know that this area is 0.9332. But that's not what the question was. The question was, what's the probability of randomly selecting a woman whose height is above 66 inches? So what's that area going to be in there? 1 minus 0.9332. Good, right? Whatever that 0.668, 0.068. That look right? Yes? Am I close? Okay, good. Okay, so you see how I'm manipulating this? The important thing is you understand how to interpret this table. Any area that you get here is any area that you find in here, if it's a positive z-score, is going to represent the area from that z-score down. It's always going to be an area greater than 50%. And if it's a negative z-score, it's going to represent an area from that negative z-score to the left again. It's always the area to the left. Okay, now, there's other ways that we can calculate this as well. Okay, if we go into Excel, actually, let me do it this way. This is on Blackboard again. If I go into Excel, okay, go into Excel, there's a whole series of functions that will help you calculate these areas. There is one function here called norm dist. You're going to see it a couple of ways. Sometimes you'll see it as equals norm dot dist, or norm, or not. You'll also see it as norm dist or norm dot dist. Right? You can see it both ways. Okay, now the difference is that over time, Microsoft refined these functions, and the later versions of Excel have used these functions norm with a dot, norm dot dist. But a lot of people built spreadsheets that use the old function, so they kept the old function available. Now, on most of these, it just calculates faster, or it's more efficient. The calculation, it comes up with the same value anyway. So for the functions that we're working with, as far as I can tell, it doesn't matter if you use norm dist or norm dot dist. It should come out the same way. So let's see what these different functions do for us. Okay, and I've kind of summarized it here. There's also a PDF file that kind of summarizes. That formula norm dist, if we put in the x value, the mean, the standard deviation, and then just say true or yes for true, I'll talk about that in a second, it gives you the area to the left of the z value. It gives you the same value we're getting off of the other tape, off the z table. Let's give that a try. Equals norm dist parentheses, and notice it comes up. You can see, on your version, it's going to be a lot easier to see. I can't blow this up. It comes up and suggests some parameters to you. The first parameter it suggests is the x value. So for the x value that we just had was 66, comma, the mean was 63, comma, now it asks for the standard deviation, which was 2, comma, and then it asks for something called cumulative. Whenever we use this function, we're always going to say yes for cumulative, right? True or yes. So I'm going to put a y in there. I'm going to hit parentheses. I'm going to hit enter. Whoops. I don't think cumulative true. There you go. It wants true. Wouldn't take yes, right? That's a logical operator. And what area does it return? 0.9331, same area we got to the left. But now again, remember that the question was, what's the probability above it? So now I have to go 1 minus, it equals 1 minus this value to get the value we're actually looking for, 0.0668. Okay, so you can use Excel to do this as well, right? You can use a table, You can use Excel, you can use both if you want to check your answer. Everybody comfortable with that so far? Okay, okay, good. All right, and there's a couple of other versions of this as well. Okay, for instance, if you calculate the z-score and you want to know what the area to the left of that z value is. For instance, remember before we had a z-score of negative 0.5? You can use something called norm S-dist. That's norm for norm and standard distribution. We'll talk about that in the future, hopefully. Norm S-dist equals norm S-dist, parentheses. All it's asking for now is the z-score. The z-score we were interested in before was negative 0.1. And I'm going to put parentheses and then hit enter. And it comes up to the 0.4. No, I'm sorry. It was negative 0.5, right? Negative 0.5. And it comes up to be on 0.3085, just as we got from our z table before. That's the area to the left of a z-score of negative 1/2. Okay, so there's two functions that you can use that are going to be are going to help you out. One, if you know the mean, the standard deviation, and the value you're interested in, use norm dist. If you've calculated the z-score and you just want to know what areas to the left of your z-score, you can just use norm S-dist. Okay, good. Now let's take a look, see if we got another example here. Okay, I'm going to skip that one. Mean, I'm checking out. Oh yeah, I got time for this one. Okay, body temperatures of adults have a mean of 98.6 degrees and a standard deviation of 0.6 degrees Fahrenheit. Find the probability that a randomly selected individual has a mean body temperature that is greater than 99 degrees. Okay. So let's get this. Again, I'm going to sketch this just to make sure I know what's going on. Get this out of the way. That's ugly. 98.6 and a standard deviation of what I say it was? 0.6. And we're looking for greater than 99 degrees. So 99 degrees is going to be around there somewhere. 99. So I'm looking for the area above here. Okay. So what's my z-score for 99 degrees? 99 minus 98.6 over 0.6. Okay, so what does that equal to? That's equal to 0.4 over 0.6 is equal to 0.6. I'm going to round to 7. Okay, that's going to be a positive number, right? It's a positive number because it's 99 is greater. My x is greater than my mean, right? 99, and we know it's to the right of the mean. So what area is above there? So what I need to do is go to my table or to my to Excel to figure out what the area is to the left here, and then subtract it from 1. Everybody comfortable with that? Look it up. You guys tell me what it is. I can't do all the work here, right? Anybody know what that area is? You got to use a z-table or use Excel, right? You're looking for the area that represents a z-score of positive 0.67. So you're going to go to 0.6 and then go to the 7th column over. Not that hard. How much is it? 0. You got to yell it out for me. 0.7486. Do you use Excel or the table? You use the table? Or use both? Came out the same, right? Okay. Does everybody agree with that? You use norm S dist if you know the z-score. You can use norm S dist here because we know the z-score. We calculated the z-score. If you want to use, if you don't want to do that, you want to skip that step, you can use norm dist and put in 99, comma 98.6, comma 0.6, comma true. Okay, you could have got, and you would get the same answer. Okay, so this area is 0.7486, and that leaves, I'm going to subtract that from 1, and it leaves 0.2514, I guess, or something like that. Right? 25%. Well, 25% of the population is temperature above 99 degrees. Okay. So, which explains why when I go to the doctor and I think I'm sick, and she takes my temperature and she said it comes up 99.2 or something like that. She says, "Well, you don't have a temperature." I said, "What are you talking about? It's 99.2." Right? Well, she's thinking about, that's close enough to a normal temperature. She's not concerned about it, right? Okay, so and a lot of people have a normal temperature that's higher than 98.6 or lower than 98.6. That's the probability of what percentage of the people in this population have a temperature less than 98 degrees. So less than 98 degrees. Okay, that's below the mean and it's to the left, so it's going to be less than 50%, right? So the z-score is going to be equal to 98 minus 98.6 over 0.6, so that's a z-score of negative 1. And that we can look up on Excel, right? I'm going to do that. Do I have an Excel spreadsheet still open? I guess I closed it. Oh, there it is. Okay. So I'm going to do that here. I calculated the z-score as being equal to negative 1. So I can use equals norm dist, parentheses, norm S dist, parentheses, and just put in the z-score, which is negative 1. And the area to the left of that is about 16%, 15.8%. Remember, 16% was our empirical formula was roughly 16%. Okay, and I could use the norm dist, and I could put in what's x. X is 98. What is the mean? 98.6. Comma. What is the standard deviation? Whoops. Comma. What's that? Why is that working? Comma. What is the standard deviation? It's 0.6. And why is that happening there? Oh, I see what it is. The cursor's in my way. Comma, 0.6, comma, true for cumulative, and hit enter, it comes up the same thing. And if I go to my table and I look up a standard deviation of 1.0, negative 1.0, negative 1.00 is 0.1587. So all three of those gave you the same value. Okay? Good. Okay, let me go back to this. I'm gonna move on to the next question. Actually, no, maybe not. Let me make sure we get this. Okay, what's the probability that we would randomly select a person that's has a temperature less than 98 degrees or greater than 99 degrees? Okay, so what is this area in here? What do we say the area below 1 was 98? Right, this area we said was 0.1587. Was this area in here less than 98 degrees and greater than 99 degrees was 0.2514. Right? So what's the probability that we randomly select a person that is either below 98 or above 98.6, not above 99? It's going to be the sum of these two areas. And what's the prop, which is going to be 0.2514 plus 0.1587. Add them together, it's going to come out to roughly 41.41, something about 41%. What's the probability that you would select the person that's between 98 and 99 degrees? Well, it's going to be 1 minus that 0.41, right? Because it's going to be area in between here. So it gets a little tricky, right? That's why it's nice if you draw it out. Yes. That's a good question. That's kind of a good question, but it's on the exam. Since the z-score, you only know the 3 decimal places, right? I would say, put in three numbers, right? So yeah, if it's a height, 68.4 or whatever, and if it's different than that, we'll give you some guidance on the exam on how many decimal places, right? So we'll give you a hint on how many you should. But one thing you should never do: don't round until you're all done. In these calculations, it's not going to make that much difference. But later on, we're going to be you're going to be using calculations where they take a number like 4, say it's 4.1, and we round it to 4, right? Doesn't seem like that big a problem. But now let's say that part of your calculation is you got to square that or cube it. So now it's 16, but 4.1 now it multiplies the error when you round early and then do other calculations based on it. You can make the error bigger. So in statistics, you want to avoid rounding until the very end, right? So keep as many decimal places as you can. And if you're using Excel or a calculator, that shouldn't be too hard, right? Just got to type in the numbers and keep track of the numbers. And Excel even will store those numbers for you. Even if you round the cell and if you tell it, only show me 3 decimal places in Excel, it keeps the entire number. It's hidden from you, but it's actually in there. So if you do calculations based on it, it'll do it based on the real number, not the rounded number. Right? So yeah, we'll give you a bit of guidance on it. In environmental occupational health science, where we do a lot of measurements of toxic things in the environment and poison, toxic materials in blood, and so on and so forth, we have a concept that's called significant digits. So in other words, if the calculation is A times B equals C, if A is only known to 2 decimal places and B is known to 16 decimal places, the answer is really only valid to 2 decimal places, right? Because it's only as good as the least accurate measurement that you're using to get to it, right? So kind of keep that in the back of your head, but we'll give you a little bit of guidance. There was another hand up back there. Oh, you mean, well, the reason why that came up is because it was actually 4/3, right? 4/3 is an infinite number of decimal places. 0.6666666, it's infinite. So at some point you got to round it, right? You got to work with it on a practical basis, right? So again, that would depend on, on how much, what other digits what other, how accurately you know the other stuff. Like if the weight is to a whole number or something like that. So it's 100, 100, 142 or something like that. You only know that to 3 significant digits. So 0.667, 0.666, 0.6664 decimal places for that would probably be enough, right? Because it would be more accurate even than your number for the weight is. Yeah. Are you saying that we're getting a different result in Excel than we are from the table? Oh, no kidding. Really? I'll tell you what, let's put that aside for now, but at the end of the session, show that to me, okay? I'll address that during one of the help sessions. Okay, one of the review sessions. Okay. It should be pretty close though, right? Okay. Let's see. Percentage of school teachers in the United States who have a mean salary 32,000, standard deviation 3,000. Okay, so now let's take a look at this now. We have salaries for school teachers. That's been a big issue lately, right? There've been a lot of strikes and labor movements, and I know the adjuncts are in an uproar about salaries here at CUNY and so on and so forth. But so salary is a very sensitive topic among teachers nowadays. Okay, but let's take this particular group. Okay, so in this particular group, the average in this particular population, the average salary is $32,000, and with a standard deviation of $3,000. Let me just get a. So I want to just draw out this distribution. So my average salary is $32,000, and my standard deviation is $3,000. So now the question here is, where'd it go? There it is. Okay, question here is, what percentage of teachers would you expect to have a salary greater than $36,500? So we're looking at the area that's above here, right? That's going to be, Z is going to be equal to 32,000 minus 36,000. Oops, got it the other way around. 36,000. Is that 36,500 or just 36,000? 36,500. 36,500 minus 32,000 over 3,000. That's 4,500 over 3,000 is equal to positive 1.5. And how would we solve that? Again, we find the area. We find our z-score of 1 plus 1.5, and it's 0.9332. So the area to the left of this would be 93.32% or 0.9332, and the area, the percentage of teachers that would have a salary above that, we would expect, if it's normally distributed, to be 0.0668, as we calculated before. So I'm gonna go off on that now, and let me give you another view of this. Okay, assume that blood pressure readings have a mean of 120 and a standard deviation of 8. What blood pressure would you have to exceed to be in the highest 10% of the population? A little bit different here now, right? Okay, this is going to be my last example here because we're going to move on to binomial distributions in a second. Okay, so let me get back to let me draw my table here. Here's my normal distribution for blood pressures. And again, I have to sneak back here and take a look. 120 and a standard deviation of 8. The mean is 120. And the standard deviation is equal to 8. And I want to know, what blood pressure do you have to be in the highest 10% of this population? So what I'm looking for is, what does my z-score, what value does this have to be in order for this to be 10%? I'm doing this backwards now, aren't I? In other words, this is the area I'm interested in. Now I need to know what the z-score is for this, right? How am I going to do that? I'm going to use the z-table backwards. But I'm sorry, what's that? Oh, let me go again. Okay, so how am I going to use the z-table? Well, for starters, the area to the left of that is going to be 90% of the distribution. So I'm going to go over here and I'm going to look. Here is I'm looking at the areas to above 50%, and I want to know what z-score would bring this shadow over so that only 10% is not selected. So I'm going to go into the middle of this table and I'm going to look for an area of 90%. So let's see, where's the area of 90%? 93, 88, 90.32, 89.80. The closest number I have is 89.97. 89.97. This number, it represents an area that has 90% of this distribution to the left of it. So what z-score is that? That z-score is 1.28, right? So the z-score that represents this value is 1.28, right? If I had looked up 1.28, I would have gotten 90% is to the left of that value. So that means that value that has a z-score of 1.28 is the blood pressure that represents the point at which 10% of the population is higher than that and 90% is lower than that. So now how do I figure what that number is? Remember that formula I had before? Z is equal to x minus mu over sigma? Well, gee, I know what z is this time, 1.28, right? And I know what the mean is. I don't know what x is. I know the mean is 120. I know standard deviation is equal to 8. So now I can calculate this because x is the only thing I don't know. So I'm going to cross multiply across here. So it's going to be x minus 120 is equal to 8 times 1.28. Okay, I'm going to move that to the other side. So x is going to be equal to 120 plus 8 times 1.28. Somebody figure that out for me. 130.2? 130.24. There you go. That's the blood pressure that 10% of the population is greater than that number. So how did I do that? I just used the Z table the opposite way. The numbers in the middle represent the areas. I could use the areas to find the Z-score I was interested in. Okay. You guys comfortable with that? It's a little bit of a twist, right? Okay, but there's some examples of this in the assignments, in the homework assignments. Plus, we'll go over this on the review sessions and stuff like that. Okay, so now let's move on from here. The next thing I want to talk about is a special version of this normal distribution, called a binomial distribution. Remember when we were flipping coins and answering questions and so on and so forth? We work with probability trees and so on and so forth. Well, we're going to kind of go back to that again. I'm going to go to, I have another document number 2, I think is where we want to be now. Document number 2. There it is. Okay, so a binomial variable is one that has 2 outcomes, 2 values or 2 outcomes. What could that be? Well, left-handed or right-handed, right? Male or female, diabetic or not diabetic, right? Those are all variables that can only have 2 values, either IR, cancer, no cancer, right? So on. So when we look at populations and we're interested in the probabilities of finding one outcome or another, that and when we're looking at binomial variables, well then we wind up in a special situation. Remember, if you recall, when we were talking about coins, I don't need this anymore. Okay, when we were talking about coins, we set up a probability tree, right? Well, what's the probability of heads or tails on the first coin? Well, it could be 50% heads, 50% tails. Well, what about the second coin? Well, second coin, the first one had been heads, the next one could be heads or tails. Or if it had been tails, the next one could be heads or tails. And then the next one could be, and so on and so forth. We set up a probability tree. It was easy to predict. If I asked you, if I flipped 10 coins, what's the probability that they're all heads? That's easy, right? 0.5 times 0.5 times 0.5. What's the probability of all tails? Again, easy, 0.5. But probabilities in between get complicated because there's so many different ways that we can have these outcomes, right? So in fact, we can either create a probability tree, right? Let's say that we're looking at diabetes, right? So probability that in this population the person is diabetic is 10%. So if I start with the first person I select, they might be diabetic or they might not be diabetic. Probability of diabetic is 0.1. Probability not diabetic is 0.9. Well, next person could be diabetic, which is 0.9. Could be not diabetic, which is 0.9. Again, and just the second person, I'm already up to 4 possible outcomes. The third person, I'm up to 8 possible outcomes. The fourth person, and another person. So I'm looking at, if I'm sampling 10 people, the number of outcomes I get gets very large. If I'm sampling 100 people, forget it. I won't have enough paper in the world to draw this probability tree. Well, in fact, it's a simple probability. You can actually calculate pretty directly what all the possible outcomes can be. And we have a formula for that. Okay, it's an ugly formula, so I'm going to flash it up here just so you can see it. Is that the one? Nope, that's not it. This is it. Here's the ugly formula. Okay, the probability of any particular outcome, like the probability of 2 people being diabetic, right, is equal to, I'm going to go over to the right side, the number of people, number of trials, the number of people in your sample. Like I said, I'm going to sample 10 people. That n is those 10 people. So 10 factorial is 10 times 9 times 8 times 7, and so on, over n minus x factorial. N minus x, that's 10 minus the number I'm interested in, exactly 2 people being diabetic, factorial, times x factorial, 2 times 1, times p is the probability of being diabetic, which is 0.1, to the x power, to the second power in this case, times q, which is 1 minus p, which would be 90%, 10% minus 1, 90%, times, and so on and so forth. So this formula is like, you could work this out if you wanted to, right? But it's pretty cumbersome. So Excel has a great way of calculating this, right? Excel really simplifies it for us because it has a binomial distribution calculator built into it. And in order to calculate the probability, we have to know the number of trials, the number of people you're going to sample, 10 people. But the example I just gave, what's the probability of getting exactly 2 people out of 10 that I select that are diabetic when the prevalence in the population is 10%? Well, for any individual, the probability of success or being diabetic is 10%, 0.1. My sample size or my number of trials is 10. The number of successes desired, that's my 2, right? 2 people out of 10, right? And so that's all I really need in Excel to calculate this probability. So I'm going to go over here to my document. And I'm going to get rid of this. Okay, so let's go in here. A study indicates that where'd that come from? 10% of nursing home patients are diabetic. You randomly select 10 patients. What's the likelihood that exactly 1 patient will be diabetic out of the 10 that you select? Well, okay, that's going to be, let's see. Well, first of all, what's the probability that all of them will be diabetic? Be 0.1 times 0.1 times 0.1 times 0.1, so on. But this idea of 1 or 2 or 3 gets a little bit more complicated, doesn't it? Okay, so what's the probability that none of them would be diabetic? Well, that would be 0.9 times 0.9 times 0.9 times 0.9, and so on and so forth. But 1 out of 10 or 2 out of 10 and so on and so forth gets more complicated. I'm going to go into Excel. And I'm going to use a function called Binomial Dist. Equals, I'm going to blow this up a little bit more even. That too much? No, it's not. That's okay. Actually, maybe make it a little bit smaller. I want to do some other stuff here. Okay, so equals binomial. Notice again, there's a dot dist or binomial dist. You could use either one. Binomial dist parentheses. It prompts me for the information it needs to do this calculation. It wants to know the number of tries, the number of successes, the number of trials, the probability of success on any individual trial, and cumulative. Okay, so I'm going to put this in. The number of successes is 1. 1 out of 10, right? Comma, the probability of success is 0.1. That's the prevalence of diabetes in this population. The number of trials is 10. I skipped that. Comma, the probability of success is 0.1. Comma, and cumulative. True or false? I'm going to put false in here. I'm putting false in because false means I don't want this to be cumulative. I only want to know the probability that exactly one person out of 10 is diabetic. I'm going to hit enter, and I get 38.7%, 0.387. That's the probability that I'll get that outcome. What's the probability that I'll get none? Okay, equals binomial dist, parentheses, number of successes is 0, comma, number of trials is 10, comma, probability is 0.1, comma, and cumulative, I'm going to put false again, parentheses. Comes out to be 0.3486. Okay, very interesting. Now, how about, well, gee, that was for 0. That was for 1. How about 2, 3, 4, 5, 6, 7, 8, 9. How about all 10? 10 out of 10. Okay. Oh, that's interesting. Let's take a look at this. I'm going to calculate this for each one of them. It's equal to binomial, a little late, binomial dist. Okay, and the number of successes is 2. I'm going to put that in instead of the actual number, the link. Comma, trials is 10, comma, probability is 0.1. And again, cumulative, I'm going to put in false. And I'm going to then copy this all the way down, and it'll give me the probability for 3, 4, 5, 6, 7. And there you go. That at the bottom is scientific notation. It's basically saying that it's smaller than 1 times 10 to the minus 10, right? 1, like, I don't know, trillionth or something, right? So look how small this is. So the probability of getting, since the probability of being any individual being diabetic is 10%, the probability of all 10 being diabetic is 0.1 times 0.1 times 0.1, which is 10, which is 1 to 10 to the minus 10, which is that number, right? So that actually comes out right, right? So what do you think these all add up to, all these probabilities? That's a good guess. Let's give it a try. Find the sum of all of these. And it comes out to, whoops, I think I screwed that up, equals sum, parentheses, of all of these numbers. Wait a second, equals sum, parentheses. One. Good guess. And so there's all the possibilities, right? Those are 1. Okay, what if I asked you, what's the probability of getting 2 or fewer people that are diabetic? In other words, out of 10, 2, 1, and 0. Well, I could just add up those possibilities, right? Equals the sum of 2 out of 10, 1 out of 10, and none out of 10. The probability that I would have 2 or fewer, or I could also phrase that less than 3 people that are diabetic out of 10 if I randomly select 10 people, probability is 93%, right? Well, remember that what we just said about cumulative? Watch what I can do now when I want to calculate that. I can instead say equals binomial dist, parentheses, and then I could say to myself, number of successes is 2, comma, number of trials is 10, probability is 0.1, and the cumulative now is going to be true. And what does that mean? That means I want Excel to give me the probability for not just 2 successes, what I put in there, but also any that are less than that, 2, 1, and 0 all added together. So I should get the same number as I got for adding up the 3 individual ones. And it does come up the same. Okay. So what's the probability of getting 3 or more successes? 3 or more people that are diabetic, if I randomly sample 10 people. What's the probability of 2 or less? 92%. So what's the probability of getting 3 or more? It's going to be 1 minus that 93%. Oops. Equals 1 minus that 93% is going to be about 7%. Okay, so we can use this binomial distribution in this manner. Yes. If you don't, I'm sorry, if you don't have. Well, you have to read, you have to interpret the problem. You have to parse the language and the problem. In fact, I'm glad you brought that up. Let's take a look at what's the probability that more than 4 will be diabetic? So what should you use there? Yeah, for cumulative, let's say cumulative, what should you, what binomial disk is equal to what number? What number of successes for 4 or more? I would use 3, right? Because then I could say 3, 2, 1, and 0, right? And 4 or more is going to be the remainder. So I guess it's just subtracted from 1. Get it? In other words, you got to kind of listen to the problem, interpret it. So in this case, it says the probability that 4 or more will be diabetic. Well, it doesn't. The function doesn't work that way. Just like the Excel function in the table only tell you the percentage below that z value, the function only tells you the probability below the number you choose, at and below the number you choose for your successes. So if you want to know 4 or more, right, you would have to say 3, 10, 0.1 true for cumulative. That would give you 3 or less. And then you can subtract that from 1 to find out 4 or more, because that's what would be left. If the next question is, oh, I'm sorry, more than 4. More than 4, you would use 4, 3, 2, 1, 0. And then more than 4 means really 5, 6, and up, and so on and so forth. So use 4, 0.1, the 4, 10.1 true, and then subtract it from 1 to get 5, 6, 7, 8, 9, 10. So you really have to kind of read the problem and understand the problem, okay? So, because depending on how the problem is phrased, it's going to change that quite a bit. Okay, so now, the other thing that goes on here, just quickly over here, study indicates 4% of American teenagers have tattoos. I'm always tempted to ask how many people in this class have tattoos. I can't do that. Sorry. Never mind. I don't want to know who has a tattoo in this class. A study indicates that 4% of American teenagers had, when I was a kid, your parents would beat you to death if you went out and got a tattoo. Things are different now, of course, but that was a whole other thing. Okay, so a study indicates 4% of American teenagers have tattoos. You randomly I also grew in the neighborhood that was almost entirely Italian and Jewish. And this was like, when I was a kid, it was like the 50s, when I was a very young kid. And there were a lot of people in that neighborhood, not a lot, but there was a significant population in that neighborhood that were survivors. So this connotation of a tattoo doesn't have the same impact that I guess it does today. But at any rate, a study indicates 4% of American teenagers have tattoos. You randomly sample 30 teenagers. What's the likelihood that exactly 3 will have a tattoo? That's an easy one. 0.4 times 0.4 times 0.4, right? Okay. 3 or fewer will have tattoos. Okay. Well, now we I'm sorry. I forgot that it was 30, not 3. Exactly 3 will have a tattoo. It's going to be equal to binomial disk, right? Exactly 3 is going to be 3, 30, 0.04, false, because we only want exactly 3, right? We only want that outcome. 3 or fewer will have tattoos. Binomial disk, binomial disk parentheses, 3, 30, 0.4, 0.04, true for cumulative, and now I'll give you the percentage for 3, 2, 1, and 0. In other words, 3 or fewer. 4 or more is just going to be 1 minus 3 or fewer, right? Which you already done. Okay, good. Now, we're not talking about Poisson distribution, so I'm going to skip that. I just want to talk about one more thing, and that is that there's another way we could look at this binomial distribution. I'm going to show you a little movie. Remember we talked about this idea of that probability tree, and what's the probability of getting all heads if I had 10 coins, all heads, or 10 coins, all tails, or 3 tails and 4 heads, and so on and so forth. This machine simulates a probability tree. It's called a Galton machine. It's been named after the statistician. This machine starts out, it's like, anybody know what a pachinko machine is? It's kind of a Japanese pinball machine, except it has like a steel ball drops in the top and it bounces around, it's vertical. Well, this is kind of like that, right? So Google pachinko machines when you go home. So what this does is a steel ball drops down and there's a pin that ball hits, and that ball can go either to the left or to the right. And then in the next row, there's another pin that it could hit, two pins, could go to the left or to the right. Each time it hits the pin, there's a 50% chance it'll go to the left, 50% chance it'll go to the right. So what do you think the most common outcome is going to be if you were to collect these balls in the bottom? How many left and right turns would be the most common outcome? Half lefts and half rights, right? So you would expect most of the balls to wind up below the ball. And the least common would be all left turns and all right turns. Let's see what happens if you actually do this. This is at the Queen's Museum of Science, near the Old World's Fairgrounds. There you go. And there the ball's coming in the top, right? Can you see them there coming in the top, hitting those pins and bouncing back, and you follow them down. This is basically the equivalent of 10 trials, right? Because each one of those rows of pins is a trial. Okay, and if we go down to the bottom, let's see what winds up happening. Well, sure enough, the most common outcome is to have close to 50-50 in terms of the number of, that kid in the back, there's two kids were hanging around there almost, for hours waiting for it to completely fill up to see what happens when it fills up. So at any rate, yeah, but I guess they weren't very busy. So if you look, yeah, exactly, we got time on there. When you're that age, you got nothing but time on your hands, right? So at any rate, so you can see what's happening there. What does that look like? It looks like what kind of distribution? Even though it's a binomial variable, it looks like a normal distribution. And we can take advantage of that. We can do calculations based on its similarity to a normal distribution. We call that the normal approximation to the binomial distribution. And in fact, in the lecture, Levi spoke about it. If n is the number of trials, the probability of getting heads is 50%. You would expect on average to get 5 heads. So 5 would be your average. Your standard deviation from 5 would be the square root of n times 1 minus p times p times 1 minus p. Right? And that would be your standard deviation. And you can use that mean and standard deviation to approximate how likely it is to get 3 or fewer or 7 or more, kind of treating it as a standard deviation. It's an approximation, right? Approximation to the standard normal distribution. And it works better if it's like 50% than it does if it's 10%, because obviously it's going to be skewed and stuff. But and if it's a large sample, but a lot of trials, but you could use that in lieu of, as an approximation, in lieu of calculating that complicated formula, or using the tables or Excel.